Which of the following is a linear unforced differential equation? You have here dy over dx equal to 0. The second derivative of x over dt and the second derivative of y over dt equal to 0. And lastly, the first derivative minus 2y over the second derivative equal to 2. So which is linear unforced differential equation? Hi, Assalamualaikum. In this lesson, you will learn about differential equations, and at the end of this lesson, you will be able to recognize the unforced linear differential equations, or it is abbreviated as a LUDE. Okay, let's start. In a radioactive decay, it was experimentally found that the decay rate, that means how many isotope decay over time, is proportional to the remaining number of isotopes. So the decay rate is represented by the first derivative of the remaining number of isotopes over time, and it is proportional to the remaining number of isotopes. And the negative means the decay rate becomes slower as the remaining nuclear isotopes become smaller. The amount is becomes smaller. Okay, so in equation form, it can be written as, so this proportionality we can convert it into the equal form, where we put a proportionality constant lambda, where this proportionality constant is called a decay rate. Okay, so we can rearrange them to be dn over dt plus lambda n equal to 0. That means we put everything on the left side, so there is nothing on the right side. This is an example of differential equations. So what is a differential equation? A differential equation is an equation that involves at least first derivative of a function, as well as possibly the dependent and independent variables separately. So that's mean in this equation, you can see there is a first derivative of n. So that's why we call it as a differential equation. Okay, let's look to the example of differential equation, which we can recognize by their order. Okay, the order of a differential equation is determined by the order of the highest derivative in the equation. For example, here here you can see from this equation, you can see there is the highest is the first derivative. So we call this equation as a first order differential equation. So if we look into the second equation, here you can see that the highest is the second derivative. So we call it as a second order differential equation. For the third, you can see even though we don't have a second derivative and the first derivative, but the third derivative is available there. So that is the highest term in the equation, so we call it as a third order differential equation. How about the equation for the decay, for the radioactive decay that we have seen it in the previous slide? So this is the first derivative. Okay, so that's why we call it as a first order differential equation. All right. Okay, now let us go to the unforced differential equation. Okay, many phenomena in science and engineering are conveniently expressed in differential equations because we are interested in the change of quantity in science. So how many this thing change with this? So that's why they are conveniently expressed in differential equations. Okay, so in this diagram, I show you a typical RL circuit where we can draw a circuit diagram like this. So it has a switch and connected to a battery. Okay, so R, L, S, and E. So okay, so when we close this circuit, so we close, so the current will start to flow. Okay, the current will start to flow, and this current change over time. Okay, so the behavior of this current in the circuit can be expressed using this equation, where L is the inductance, di over dt is the change, the rate change of current, times the multiplication of resistance time R, and this is the voltage. Okay, so I write it down again so that you can see that the I is dependent on time. Okay, so terms that involve I is collected on the left side, while the other is on the right side. That means the current we put it on the left side, other which is not related to current we put it on the right side. Okay, the term independent of I, which that means the thing that the quantity which is not related to I, which is here is a voltage, is put it on the right side. Okay, when we have this kind of equation, we can say that this is a forcing term. So this everything on the right side is a forcing term. Forcing term is something which give a external external push to the system. Okay, so that is what we call a forcing term. So if the forcing term is 0, so suppose that this is equal to 0, then this equation we can call it as unforced differential equation. That means if there is no forcing term, so the equation equal to 0 on the right side, so that equation it is called as unforced differential equation. Or there is another name for it, it is also called as homogeneous equation. Okay, so an example of unforced differential equation is simple harmonic motion. Okay, so the oscillation of mass spring system, where we have a spring here, and then we have a mass. So when we release this mass, so it will if we ignore forcing term, that means we ignore anything, so just pure motion, so this mass will oscillate freely. That means there is no forcing term, so it can be expressed using this equation. Okay, so the second derivative of x over m dt is just a, right? This is force. Acceleration. So the net force acting on this mass is F equal to ma equal to minus kx. So this is a Hooke's law. Okay, the net force is equal to Hooke's law. So we can represent this into this differential equation. It is just arrange the terms. Okay, and then if we put everything which is related to only the displacement on the left side, so that we have like this, that means we don't have forcing term equal to 0, where k over m, maybe you can relate it in your previous lesson in vibrations. So omega square equal to k over m, so this is the angular frequency. Okay, so when we equate equal to 0, so when we have this form of equation, we got it as unforced differential equation. Okay, let us return back into the answer of the teaser. So which of the following is a linear unforced differential equations? Okay, LUDE. So which one? Okay, so this one is a LUDE. You can say LUDE, and this is not, because why? Because it involves two different things, two different function. Okay, so this is not a linear unforced differential equation. Okay, so this is okay. This is okay. This is not okay because it has a forcing term. Because if we rearrange back, dx over dt equal to dy over dt. Okay, so they are a forcing term on the right side. Okay, this is a tricky. You have to rearrange into the standard form. Okay, so that you can recognize that there is a second order differential equation. Okay, so it is okay. So this is okay. It is a linear unforced differential equation. So that we will learn this the solution to these two equations in the next lesson. Okay, bye.